Okay, Rajan, let's go. So today is
Okay.
numerical relativity, and I believe, based on what you're saying there, that you have a PowerPoint presentation which goes into, I suppose, related work and then your own work. Is it?
Yeah.
Okay. So do you want to kick it off? And then when you're done with this, I will. I'll show some work that I've been kicking around.
I don't know
Um,
if there's some echo. I don't know why there is an echo, but
is there an echo from my end, or you? Like when I'm
yeah,
talking, it sounds like there's an echo. What if
yeah,
I unplug this? Is there an echo now?
yeah. It's still there. I don't know.
Oh, okay. So
It's
I
still
can
there.
leave this in then probably. Okay.
Yeah.
Yeah. So I've done some simulations as well with numerical relativity. Kind of interesting in that they're still quite rudimentary, but with time, well, so one of the things I'm looking at is instead of just looking at spherical objects in space like planets, looking at more obtuse sort of objects like the platonic solids, um, what the shape of the gravitational field might be in the presence of, let's say, the Borg cube, something like that. Um, but it's still a work in progress, so maybe we'll be able to see. How does that work when you mute yourself? Did you get rid of the echo, or?
No, it's still there.
Hmm.
Uh,
I'll try muting myself. And do you want to
oh, it's
talk?
repeating. Something is repeating. I think it's following. I don't know why. Let me check my.
Okay, so it's still there even when I mute myself, is it? Oh, battery's running low. Oh yeah, that's probably the reason. Okay. Can you share your screen then, Rajan? Or do you need? Oh yeah.
Yeah. Maybe.
Sorry, I
You have
have
to
to
put
add it.
me in.
Yeah,
Yeah, you have
sorry.
to add it. That's the only problem.
Okay, yeah. I thought you were able to do that yourself. Okay, so you're sharing your
Yeah.
screen there. So
Can you
uh,
see now?
yeah,
Okay.
yeah. This is very like what I'm doing. This looks a lot like it, my work.
Okay.
So you have a number of slides there, 36. Oh yeah,
Can you
you can
see
do it
now?
in like, yeah. You just want to go into the presentation mode or whatever.
Okay.
Okay, we've got the same problem that we had last time. Do you remember how you fixed that?
Let me see 1 minute. Okay.
Yeah,
How is? Okay.
yeah. I think this is the route to go. There we go.
Is it
All right,
better?
looking forward to
Is it better?
this. Yeah, that's it. That's
Is it okay?
perfect. And yeah, that's
Okay.
it. I'm gonna mute myself and I'll just listen.
Okay. Okay. So one of the things, the main thing aspect is we are going to look into the state of the. So one of the things is okay. Yeah. Okay. So the state of the numerical relativity. See, this was interesting for Christopher and me. I presented this in the history of physics, the 10th episode. We advanced the history of physics from Galileo onwards to the present time. And as a natural evolution of that, the natural evolution of Okay. So essentially, what happens is that the history of physics, uh, we said that the problem with the general relativity is that it is not, it's a mathematical equation, but something very hard to realistically find out whether it's true or not. And that's true with quantum physics because too much of math.
Hey
So
Rajan, how's it
I think
going?
it's a problem. There's a real problem with the echo, I think, because it is repeating
Okay.
after me.
Yeah,
Yeah.
that's gonna throw you off. So, excuse me. What I would suggest is to do you have other devices connected to your computer? Like, uh, oh, hang on a second. I'm getting a bit confused because I'm seeing your screen. I'll just remove that for a second. Um, so you've got different devices connected to your computer, do you?
I have one
Or
extension of the thing because
um,
this problem was not there before. Let's see. Can we? Can I leave the
do you want me
studio?
to
Come
start
back?
off and then I can start off
Maybe I
with
will
my
come
work
back.
and then we can come back to your presentation later when you see if you fixed it.
Okay.
All right, let's try that. Ah, oh yeah, he's logged off. That might be another way to do it. Which window am I going to share? So is this one? Okay, you're back.
Okay. I
Have you?
think it's okay. I think it got fixed. I think because something
Okay,
else was running in the background. I think it's okay now. I think.
okay, great.
Okay.
So
So let's start. Let's start over. Okay.
sure.
I think it's okay.
Okay, I'm going to
Can
add your
you
thing.
put me? Yeah. Thank you. So let me go back here.
I wonder if this works. Oh no, that's not good.
You can hear me now, right?
Yeah.
Yeah. It takes a couple 1 minute for me to adjust this stuff.
All right. Do you want me to mute myself, or do you want me to talk as you're doing it, or?
It's not affecting. I think it fixed itself. Okay, now I think it's
Oh,
okay.
yeah, but
Uh,
do you want me to wait until you
yeah,
finish
if you
before
want
asking
to, yeah,
questions, or can I ask
yeah, yeah,
questions?
yeah, yeah.
Okay, cool.
Yeah, I think. I mean, if you found, yeah, I think maybe I'll just go through it and then you can ask questions later. Maybe
Okay,
that's
yeah, that's fine.
so I
Then
can
I'll
finish it
mute
faster.
myself then.
Okay, thank you. So essentially, what I was talking about. Sorry that we had a little technical difficulty, but is the is why the numerical relativity is important. So I'm trying to put a few words or few sentences so that you can understand that. As we know, Einstein developed this one, and it was very, very, very thing, breakthrough in physics because his equation, general theory equations, was the most successful of all of them to describe the cosmological aspects, all of the different phenomena. But of course, experimental verification was difficult because you cannot solve this problem. in any closed form solutions. So you cannot get any results out of it, any application. So of course, Schwarzschild came up with the metric, and that helped. Of course, he developed up the black hole and things like that. And a few other people, Rensler, they tried some metrics, but the problem was that again, you cannot solve them completely. So we don't get much information other than Schwartz metrics and things like that. So the relativity, the numerical relativity is uh, meant to solve that. There is a fundamental problem with numerical aspects. Uh, Let me just point out that, and that is because if you have a if you have a mathematical formulation that is a closed form, uh, that gives the actual physics of it, like equation of motion or action, things like that. Now, when you convert into a numerical equation, you lose some of the main crux, the properties of that, what it describes, the trend, things like that. But right now, the numerical relativity has increased, because of the errors, and you don't know what these errors are, things like that. But with the new way of computing and everything, this has been resolved by for a large degree, and it gives a pretty good results that you can check with the actual experimental data, things like that. So that's what I'm going to talk about initially, or the people who have attempted this. And let me start with the first one. So the numerical relativity is the field of solving Einstein equation through computational techniques. Uh, for example, gravitational interaction of matter in black holes and neutron stars, gravitational wave cosmology. The new development, the arrays for numerical computation solutions. So these are the some of the references here. People are attempted this. Uh, so the Einstein equation, basically, we know about them, uh, but with supercomputing, the complex system of binary black hole, etc., could be resolved. And the key concepts of the numerical relativity describe how matter and energy determine curvature. So the understanding of curvature is one of the things. So we use numerical grids to discretize space-time. And now people think that discretization of space-time is very important to connect quantum mechanics and relativity. As we know, that's most important, the cutting edge of the thing. That how do you describe the entire realm of the physics, from micro or the quantum level all the way to the astrophysical level. So this is the attempt. Because when you go to black holes, also the quantum aspects become important, singularities to solve the singularities. So again, quantum and the relativity are coming together. So the quantum gravity is the big thing to explain the gravity itself, because gravity is a local phenomenon. So this is where the discretization happens. As we know, the Einstein field equation contains this G mu nu, the general equation, and I'm not going to stress tensor things like that. So one of the ways to do the numerical relativity is to break it down into spatial slices involving time. So this is ADM or BSSN formalism. Uh, I will give some other references at the end to this one so that I can move on, because there's lot of work on this, so it will take forever to complete that. So I'm trying to put a gist of that and compress it into simpler means. So BSS formulation essentially is it's an evolving equation conformal factor and varies. So it's essentially discretizes into alpha Aij, where Aij is the field aspects. So, so essentially we have an equation, output gravitational wave expressed through while scalar sigma, which is psi 4 in terms of the observable strain. So you have this is described by that uh, by H, which is the integration of this spin-weighted spherical harmonics. So there are a lot of jargon in this thing. I'm trying to just point out that, and I'm going to go into details of the mathematics of that. But these can be used for interpreting LIGO, Virgo, and Kagras. As we know, these are highly complex things, and the graphics are more important. I'm going to show some graphics. So it helps in the calibration. Simulations extend to match ratios up to 10. Um, and what happens is that the black hole mergers allows simulation of binary black hole mergers. So that's the idea of predicting gravitational waves. The detection of gravitational waves, as we know, the LIGO and the Virgo are the main techniques by which it is done. So we get a lot of data from them, and also neutron star mergers. So one of the things that numerical relativity was successful in more was the detection of gravitational waves were matched with the model prediction. So the model predicted some uh, waveforms, and GW150914. This is one of the, these are the names that's given to detection. That's LIGO and the, uh, you know, Virgo. Those what they detect. For example, what they detect is are these type of thing. These are the codes given to the star or the black holes, neutron star, that they detect with these high level telescopes and all that. So they are detected massive black hole merger, unique traits. Uh, so the numerical relativity is very helpful in in this regard. So some of the videos are here. Uh, I'm not going to play the video because it will take a long time to figure that. At some other point, we can go through them. But I just want to give a gist of what it is capable of, the numerical relativity. And there are finite difference methods for approximating and discretizing space. As we know, right now people think it's a granular, space-time is granular. And one of the reasons why it's granular is that how do you distinguish between a pure energy and particle? The particle, by definition, is a discrete thing. So how do you get a discrete thing out of what we call a continuum? So really, the real observable universe cannot be considered as a continuum. So we have to consider as granular space-time or discretized space-time. So there are some spectral techniques like Fourier or Chebyshev expansions, uh, and right now we can get very high accuracy. There is a mesh refinement, resolution of the computer linear regions of interest, near black holes. So you can get the space-time as like a matrix of this grid matrix thing. So the detection of gravitational waves opened a new observation window. Numerical relativity are used to model waveforms, events like black hole mergers, things like that. Precise predictions. So it can give precise prediction for gravitational waveforms. So we see how the model predicts and see how the actual observations, we compare them, and that's how we figure out whether it's useful or not. Uh, so it can predict the dynamics neutron star as well, along with the black hole, stellar collapse, and all those events. So this is one example of gravitational wave uh, astronomy, where we have quantum gravitational wave propagation and amplitude. Very simple one, but when you convert to space-time curvature around a black hole, gravitational potential model, uh, it represents the space-time curvature, and you can see distorts the grid. So the grid is distorted and the effect is simplified version of the Schwarzschild radius. As we know, we don't know I don't think we know yet whether it's a spurious effect out of Schwarzschild matrix or not. But black hole is something that's accepted now, and even in the terms of dark matter, dark energy, the black holes come into picture, and they may all be some kind of uh, exotic matter type thing. So that's what it is. Okay. The important thing I want to point out, and this is where I think numerical relativity has been successful, is to come up the understanding that the space-time has kind of some kind of a memory. That's that I want to emphasize. Maybe where the numerical relativity may be useful and may become the key thing because it is not there in the original Einstein general relativity equations, but this they have found this memory effect. So, what is space-time memory effect? So, GW means gravitation wave. Memory effect is a permanent change in space-time geometry caused by passage of gravitational radiations. So, this memory is encoded in space-time, so that and I believe my research, I'll show you a little bit. It's ongoing research. It's called quantum cellular automata, things like that. Eventually, uh, that shows that initial the early universe could have been, uh, could have been uh, something else like hadrons, things like that. But they had they they developed into like a lattice type network, highly symmetric. So this is where the symmetry comes to picture. And this actually had encoded the memory. So the memory was there, and this memory, as we know in our own self, the memory is a very important part. So and it's like a recording, and then it can be replayed, and then that produces a special type of effect that we can, and this is measurable. So strong, like a gravitational event, test masses do not return to original separation. This is one of the aspects of the memory effect. We see, even when I studied material science, I saw the shape, it's called a shape memory, that it retains something that happened at a later time. So we can access this. So it essentially means that it's not fully removed. Like as time progresses, it doesn't erase the complete thing. There are some things left over. And this is kind of the memory. Undergoes a non-oscillatory DC offset. It's not a detector artifact. So they have eliminated the possibility of whether it could be a detector artifact thing. They have already taken care of that. So many errors come, you have systematic errors and, other types of errors that come up, but like instrumental errors, things like that. But there are ways, techniques to remove and see whether, are these artifacts of that or not. So that way, there are techniques to do that. And using that, they said it's not. They have proved that it's not a detector artifact. It's a real geometric effect. So, plain terms, space-time remembers that a gravitational wave passed through it. So, and many people are, in my recent what I call a Turkey conference, ICFAS conference, there was a person who said that his memory is encoded in many of the trees, all the plants, and other things all over the space-time, all of the environment has these relics of that. I also kind of bring out that, and my papers, ongoing papers, will look into that a little more. But mathematically, gravitational waves are usually described by the strain. So you have the strain, and from the strains, you can figure out there's memory effect or not. So the memory effect corresponds to change in the strain. Okay, so this is the limit. And if it's not equal to zero, then it means that there is a memory effect. Okay, it appears as a string. So unlike oscillator waves, HT does not return to zero. So if something doesn't go back to the original one, which means that it is keeping some leftover effect, and that's what the step-like offset is also called as a non-linear Christodoulou memory. Okay. Why is it intrinsically non-linear? So that's the important aspect. It's not a linear phenomena, and that's how we can figure out. Uh, there are two types of gravitational wave memory. Linear memory, primarily due to unbound matter, like a mass ejection process. The non-linear, due to gravitational waves sourcing gravity themselves. So it is you know, it's an action after reaction type thing. Uh, so in this case, the stress tensor of the GW not equal to zero. It's only in full general relativity cannot be captured by linearized theory alone. So NR is essential. So here the numerical, when I say NR, that's the numerical relativity, short form, acronym for numerical relativity. And that is essential to for this memory to be shown up. And I will show some graphics of what is available, a sample of the graphics. So how does it capture the memory? So the metric G mu nu, we know, it's a formulation like BSSN, I showed you earlier, BSSN form. NR would compute a Weyl scalar, like I mentioned. So the psi four is is a differential of the real and the imaginary part of the strain. To get strain, we have to integrate it over time, and the memory appears naturally within this double integration as a non-oscillatory component. So it's a non-oscillatory component and non-linear effect. Quantitative binary pattern equal merger, delta H memory has been measured to be about minus 22 to a minus 21. So these are very much in the detection scale level. How that is observed, not directly. It's not possible to observe directly. Indirectly, data analysis of the LIGO templates and statistical evidence has pulled out this aspect. So these are some of the ways we can figure out strain versus time with memory. So for example, this is the oscillation we get normally, but if there is memory, we see that there's an offset. This offset is the red one is what is the memory left over in the space time. So without memory, we'll get oscillation like that. With memory, we get a stepwise function like that. And same way here, uh, and then horizontal position, we can see that the memory puts some nonlinear term in there. Okay, another one is here, the oscillatory waveform and step-like non-oscillatory rise after merger. So this is like you said, the black hole mergers, uh, and it has shown the final offset is the memory effect. It has shown that offset occurs in this one. So we can calculate the delta H, and using these, the pictures show these one for different uh, measurements of LIGO and Virgo uh, of different neutron star. These are all coded for black hole mergers, uh, different measurements using the LIGO and Virgo. So you can see the normal figure as well as the one due to memory effect. And you see that you cannot, by any of the, you can remove that. So it's a real phenomena. The memory effect is a real one. So uh, what happens here again? We can do separation of oscillatory memory components. Again, one counts the oscillatory part, and as we know, the oscillatory part. The another curve shows the pure memory. You can see the memory as an offset here. So in all of them, we have separated here, and the memory is very very significantly. But it shows up only with numerical relativity. That's one. The other one is the memory here. You can see the memory effects here. that I showed before. And here is more detail about that. The dominant radiative modes carry oscillatory energy. Memory is strongest in non-oscillatory modes. So it works as a non-oscillatory moves. You can see these are oscillatory moves and these are non-oscillatory. And the step function is due to the memory effect. Okay. But there are challenges in numerical relativity. Uh, and simulation is computationally intensive, requiring high performance supercomputers. So, of course, supercomputers are improving and they're more advanced. The Chinese have high level supercomputers, and then hopefully quantum computing and other aspects may come from that. And with the AI and everything, we may be able to shout or filter out these effects more clearly. So constructing initial data is very complex. You have to choose initial condition, the match expected physical configuration. Error analysis is very, very important. See, in any numerical techniques, error is the biggest problem, and you have to account for that. Do not introduce significant error. You have to ensure that, especially in your singularities or events erases. That's a challenge, ongoing challenge. And uh, these references give all the details of those. Okay, so conclusion has made groundbreaking progress in the gravitation phenomena. And emergent contemporary ongoing episode of numericality continues to push the frontiers. So this presentation includes the key concepts. Uh, okay, so these are the references. You have many references, and specifically numericality foundation references are these: solving Einstein equation, computer, and then many others. And then you have some key references shows about the memory, nonlinear nature of gravitation wave memory effect, gravitation wave extraction of gravitation wave nonlinear effect. So these are the main things. So now I'll show you briefly. It's an ongoing thing. Uh, my quantum cosmology aspects. So early universe, which I published end of last year in Open Journal of Astronomy. I use that the gravity is not a fundamental phenomenon. Magnetic thing, the superluminal condensate. I presented one a few weeks ago, beginning of this year, about this in more detail. But I'm going to pull out some salient features, which brings out the numerical aspects of this one. So we know about Einstein metric and things like that, ds square, and this is often used in many forms. And here I explained this in more detail in the other one, but also in the paper. It's all there in the paper. So it's a magnetic field strength. Essentially, I'm trying to show is that the magnetic field can bend space. It's not. I don't call it space time. The superluminal content is a condensate, so it's a general cogmare. But this magnetic thing locally, essentially, you have North Pole and South Pole going at random. We talked about, but at some point they start coming together and they lock in and create this dipole aspects, right? Called Horde, and this locally then creates a specific type of magnetic field that can bend. I call it extend. That condensate as an extent. So the locally they bend them, and that creates the gravity. So this is the essence of the thing. So here we actually discretize these aspects. That's where the numerical relativity comes into picture. So we convert it to 1b square by 4. So again, I'm going to go into detail about that. It converts into Euclidean geometry, and we can get this metric uh, in a discrete form or numerical form. And that helps to plot this one. So essentially, this is a numeration of that, and you get how that magnetic field bends that extent, the superluminal condensate extent, or it creates essentially a space-time type thing. Okay, so as the magnetic field increases, the bulge also becomes steeper, and this is without bending without mass. That's very very important. So there is no mass to start with. So it's just a magnetic field, massless bending. And here the superluminal again. These are all numerically adjusted values. The condensate energy density versus velocity. So you can have superluminal velocity here in this case. And production of baryons uh, mentioned that you have to have a critical one above a critical range. The baryons start, and that's how you get the baryons or the protons, which are the most stable particles uh, from the creation and up to present time. Essentially, hydrogen and its isotopes. That's the fuel for the stars. That's there everywhere in our body. Everywhere is there, part of the water. Uh, so barium production rate exponentially drops below 1. So these are all numerical techniques that help to uh, produce these graphics. Okay, and the temperature aspect. Again, here also inversely with mass, how the emission scales inversely mass and the Planck scale level. All these are again graining space-time or discretized space-time. Okay, so the next one, this is a present paper I have. It has passed through and it's in the Galley proof range, so it should be published pretty soon. It will be published in this one by Physical Science Biophysics Journal, and I already have the reference here. It will be published within a week or two, I think. But it's already. I had to go through the Galley proof to ensure that everything is okay. Uh, the main phenomena there is a continuation of the previous one, essentially continuing from this early release. So this is create that, and then I go on to describe how it can create something called quantum cellular automata on discrete space-time. So essentially like a lattice formation. And then I expand on that the next paper, and there will be a couple of papers and move on to time. So then I'll describe time, which I say is a rank 6 tensor. It's not the time that it has both uh, tensor and scalar aspects. Time has both. And that's how you connect with the quantum aspects. The future, how the future comes, is because of the fact that there are things already up there. There are multi possibilities, probabilities, and then it collapses with this gravity that's created from the magnetic thing, and these two act together like a entanglement type thing, and that creates the real universe, and the time advancement of time, and then that becomes scalar in this case measurable time, and we measure time with clock, right? um, so that's why you call it clock time. All right, so in Goddard normal discrete action is given by this one. Again, you can see it's a discretized equation, t plus 1 t. So we are using again numerical aspects here in this case, but it's more like quantum cosmology than the pure relativity, of course, in this case. Discrete Lagrangian. So it's essentially a discrete Lagrangian with cellular automata. Uh, L-dependent micro-macro crossover. So essentially, cause graining, we get this entropy effect. Critical scale, the entropy production vanishes, reversible. So it will become reversible. So here it becomes reversible. That's why I believe that, from this I show that below the length scale of 10 to the minus 15, somewhere in the atomic range, we have a possibility of time reverse aspects. So called time reverse micro. I go into detail in this one, in this paper to some degree. So above LC entropy. So why the macroscopic curve is irreversible? We see the time passing at even, it's irreversible. We cannot go back uh, in time, like we want to go back to 1960s or 2000. We cannot really go back. Why? Because above the thing, the entropy increases. As we know, time is very closely related to entropy itself, and the emergence so irreversibility happens due to loss of microscopic information. I go into detail about these things there and how you get the microscopic information that's encoded is lost, and that means the entropy takes over, and the crossover occurs from uh, I call it microcircuit where the time is reversible to a macro circuit where time is irreversible. So we can see that it become at this range, time becomes irreversible. Okay, so the phase defects in 2D micro. So what causes this irreversibility is creation of defects. So you have the space time. It creates defects, which makes it go. And I study a lot of that in material science as well. We have dislocations, or you have vacancy, dislocate. These are all defects that makes non-ideal crystals. So that creates a flow itself. That's why we can make iron, for example. If it's a single crystal, we cannot make into structures that we want. We cannot shaping of these metals depend on this defect. So they lower the strength, the tensile strength, things like that, and then it's malleable. It becomes malleable, and that's how we get very similar space time. Uh, Cross-grained evolution produces phase defects and vortices, jack that emergent macroscopic circular may absent in the microscopic. So in the microscopic level, it's not there. When it becomes macroscopic, the defects start coming in and they lock in. So you can think of like a lock-in mechanism at each stage. Like you say, monopoles, and they lock in, they create dipoles. The same way, the defects lock in the the space-time granularity, and you get this moving thing, including life forms and all things eventually, right? So vortex defect emergence. So this is a nice picture that it kind of uh, gives an idea of how the defects work. Okay. The other one is the vortex lines and monopole-like defects, 3D quantum lattice. So these are 3D version of that, uh, and then three-dimensional quantum lattice. So quantum cellular automata, I believe, is like a unit that develops over period, and that adds to the space. That is what accretion of space-time events is generating. So you have that and movement, and they eventually create all this from the stars, planets, and then you have all the features within the planet. Um, the fractal theory says there are fractals even, uh, including human life forms or life forms in general, plant and animal life forms. So it's very interesting. I think eventually, if we can understand this a lot more, we can probably go from the early universe all the way to present time when the living organism happened. Perhaps if we can extrapolate that, we can understand what's going to happen next in the human revolution. Already we see that humans have created AI with humanoids and other things which will have probably acquire higher intelligence even, and that maybe push it to the next generation of evolution, perhaps. Uh, when microcircuit elements measurement induced decoherence are introduced. So certainly a decoherence, as we know, entanglement decoherence, well studied subject. Because of the environment, decoherence occurs. So essentially it's a coherent thing initially, but as soon as environment is introduced, it produces decoher. decoherence. And this is the biggest problem in quantum computing even, right? So qubits, for example, they get decoheres very fast, and that's the biggest problem. Essentially, a noise, development of noise. So topological defects stabilize as vortex lines and monopole structures, powering persistent, irreversible microscopic degrees of freedom. So that makes it irreversible. So how the reversibility becomes irreversible, and this is a CPT problem even uh, that I kind of mention that and see whether and possibly the quantum cellular automata may solve that problem. Okay, the future direction numerical relativity. So next generation simulation, computation for simulation is expected to become more accurate, be able to model more complex systems. The gravitational wave precision enhanced simulation will improve the precision of gravitational wave signals, leading to better astrophysical observations. Exploring exotic objects. Future simulation also investigate phenomena like wormholes, exotic stars, and quantum gravity effects. So these are the possible things that we can think of the future direction. Okay, thank you very much. Okay, all right, thanks.
Thank you. That was very good. Uh,
Thank you.
enjoyed that a lot. Um, interesting presentation, Rajan, with a lot of research there. I think different. How do you say? A lot of different references and related work. So it's pretty interesting. Well,
Thanks.
I suppose we could go through some of the slides. Maybe I could ask a few
Okay,
questions. Yeah, it's probably
should
the
I put
best.
it back?
Yeah. Sorry, I removed it.
Okay, let me check. Yeah, you can put it back. I think.
Okay.
Yeah, let me go back in there. Can you see?
Yeah, I'm
Is
sure
this
that's
okay?
fine the way it is.
Yeah.
So if we go
So
through a few of these, or maybe
should
it
I
would
go
be
back to the full thing or
yeah,
just use
maybe
it
yeah,
as
do go back to the full thing. Actually, it's just easier to
okay?
read. So I think I'm coming down with a flu or something. So
Oh, you
uh,
are?
yeah,
Oh, yeah.
hopefully.
I had. I'm still persisting. It's like many weeks.
Already, what's
Uh,
the weather like where you are? It's been cold, but it's getting back, or it's been quite warm, or
yeah, it is cold and hot, hot and cold. Like 1 week it will be l- fairly cold, and then it could rain. It could fall down, uh, plunges to 60 to 70. Of course, I'm talking about Fahrenheit.
yeah.
Then like this week, like 80s, almost like summer, 85, 84, 85. And this, tomorrow supposed to be very hot, like almost 85, very high, almost like a summer. Then it comes down again to 70, 60. So it is going up and down. It's a lot of fluctuation or oscillation, temperature going up and down. And
Hmm.
that affects because you have viruses and many people are this year a lot more than previous years. Many people, and I also eventually got it. I thought I had the flu shot and everything, so I was not initially affected, but I eventually got to me. And it has me many weeks, and only now it is in the training phase because I used to have cough. In some other presentation, I had to put mute because I feel coughing. I think today I could go through it, so I think it's in the last stages. But I do see in the night sometime once in a while you have dry cough coming up out of nowhere. But I
Hmm.
think it's reducing a lot. But there's an effect that lasts a long time. Previously maybe 1 or 2 weeks. Now it's like a month or even
Right.
more.
Yeah, yeah. Well, I just
So
feel, yeah, if I am coming down with something, it's like just beginning. So hopefully it's not as bad as that. Okay, well,
okay.
let's try. I'll go through this. Just take it easy, I suppose. And this was all fine. The next part and that, uh, yeah. fine. And then so you got this a Weyl scalar, which I assume is produced by what, a double integration or something, or
Yeah,
it doesn't
yeah. So
appear to
double
be.
integrate.
It's got h and then minus I h.
Yeah, two different times. Yeah, time
So
advancement.
right, but ht looks like it's an integral. So would that not be the scalar or?
Yeah, that's a strain. That's how we measure the strain that I show here.
Oh yeah, yeah, that is the
The
strain, isn't
strain
it?
value somewhere I show the strain value 10 to a minus 22.
Yeah, yeah, I know. So that's related to the memory effect, then, isn't it?
Yeah, it is a yeah. See HT and you find delta HT, and if it's not equal to zero, then there is a memory effect because what you are measuring is a strain over a period of time, and then if it doesn't go back, the strain doesn't recover, means that permanent strain. That's a memory effect. So
Yeah,
essentially,
I thought the memory effect was really interesting, actually.
yeah.
In the
Should I
graphs that
go
you
there?
showed for it. Yeah, absolutely. Because you have this oscillatory mode, and then you'd
Yeah.
expect it to just be flat, kind of, but then we
Yeah.
notice this increase.
Yeah, the
So,
HT does not return to zero. Yeah, it's a step-like offset. Like that's
yeah,
mostly.
and that's what we observe in the actual the waveforms, the mergers. Yeah,
Yeah, this is the one 10 to a minus
yeah,
20, 10 to a minus 21. Uh, that's the strain. The binary black hole mergers. They have measured. This is predicted by the numerical relativity, and it has to be measured as well. So it shows some you know verification, kind of, at least
yeah.
partial verification
It
of
is
that uh,
interesting, isn't it?
of the model of this model. Yeah. So
And so
just
what is
got
it
the
suggestive of? You have these mergers, and then, well, you wouldn't expect the space time to go back to normal, would you? Because now you've
yeah,
introduced this black hole singularity.
yeah,
Um,
like this one. Yeah,
so,
actually, only this numerical relativity is showing up that, not the original Einstein equation never predicted any of these things. But the
hmm,
numerical relativity has pulled out the fact that there could be this space, when they did this mathematical analysis, they said there should be some kind of a memory effect out of that. And they indeed measured that, you know. So with all these different, what you call, oh, uh, so I showed that different types of measurements. So I
okay.
think
So if
on
we
that.
go, yeah, if you go those graphs as well. Okay, so then we move on to your work, I guess. This
Okay.
kind of covers all of that, doesn't it? Yeah.
Yeah. Yeah.
And then this
This
was
one.
very interesting. So you've got
Yeah.
t, the time, and then you've got radius and phi and z. And so those are like your cylindrical coordinates, actually.
Yeah.
And
Yeah.
then
Yeah. Exactly.
you've got lambda squared. That's a cosmological constant, then, is it?
Yeah. Yeah.
Okay, because that's fairly important
Associated
to
with
know.
the magnetic. Yeah. Associated with the magnetic. Yeah.
Right, because
It
B
depends
then
on
is the
the
magnetic field,
yeah
yeah?
magnetic field. Yeah.
And so is the cosmological constant can be interpreted in terms of the magnetic field. Is that a thing?
Yeah. So the space-time geometry we can convert to this cosmological. So it increases to one recovering flat extent. So whether it's flat or not
Yeah.
is the thing. So if it is not equal to one, then it's not flat. As r tends to zero, then it becomes flat. The space becomes flat. Otherwise, it's not flat. So in this case, in general, it's not flat. So which means that the magnetic field is bending it. You know. So in this case, gamma is not equal to one. So
All
which
right.
means that yeah, if this is go to zero, b go to zero, then equal to one, then it's a flat space. But this b starts curving it. Uh, when you add b, one plus something you get. So that curves that shows the curvature. It's not flat.
Mm.
Uh, so this you can figure out by using this technique, the Euclidean geometry, and comparing them. You can figure out. That's how you get this answer, b square, and then you plot it. You get this. So again, these are all numerical techniques. So so you see that locally you can have this bending, and as you know, when you bend, you get gravity, the gravitational effect.
Yeah.
So, like Einstein predicted, the bending of space-time is what creates the gravity. So, gravity could be is not a primary effect; it could be a secondary effect of these bending aspects. And
Hmm.
once you have gravity, then you have formation of all the particles, you know, including strong field and everything, depending on the level of thing. So that's what I'm moving into. And what locks the mechanism is a quantum cellular thing that I talk about a little later. So these are
Yeah.
supernova things, faster than speed of light.
Wait, go back to that for a
And
second. Oh yeah, well, there's a question on the previous. Why are you using cylindrical coordinates instead of like spherical coordinates?
oh, so to see the curvature bending,
Yeah.
the cylindrical coordinates are much better because you have rotation, happening in this case.
Oh,
So
yeah, yeah.
it's a rotational effect. It's a rotation effect. And the rotations are best described by the cylindrical coordinates than, you know, than a normal thing.
Really.
Uh, although in this case, you can say it's a normal equation. It's a normal equation,
Yeah.
but it has a phase answer, a phase uh, addition to it. That's all. But these are all normal Euclidean thing, right?
Okay.
And then, so it's a cylindrical coordinates in general. So cylindrical coordinates has both. It's not a spherical coordinate. It's a cylindrical coordinate. The cylindrical coordinate has both translational as well as rotational aspects, right? Because cylinder is so lengthwise, it's
Yeah.
normal, yeah, Euclidean thing, and then you have this cylinder, like a circle, cylindrical thing, which is towards the rotation thing. So it has both the translation as well as the rotation aspects.
So
Whereas
is
spherical,
the idea of the cylinder is like slices in time, like as you move up,
yeah,
or
yeah, yeah. It's a
okay.
slicing
So
method,
in
which
a
is a
sense,
numerical
you're
technique.
down one dimension. The curvature is like on on a rubber sheet in a sense, rather than in a 3D space. And then you have
Yeah,
time copies of
yeah,
that along the cylinder.
yeah,
Oh, that's
yeah,
very interesting. So that's a bit like anti de Sitter space in that sense. The way it's a
yeah.
column of
It
times.
will be, yeah, yeah,
All right, and then this Melvin's metric. So that's a big thing, is it?
yeah,
Occurs a lot.
yeah. That's the one that he has really solved that exactly, and uh,
Yeah.
you can see the metric and also the graph very clearly.
All right. So
So
this
that's
Melvin space thing. That's very interesting. I'm not.
yeah,
Uh, yeah, I don't know too much about this. So then, how do you bring this superluminal aspect into it? I'm not sure I follow that part.
this one.
Yeah. So you've scaled things, is it, to different
Yeah. So you have
and
the rho, which is the energy density matrix, right? The density matrix.
yeah,
Uh, you can. It depends on the strength of the magnetic field, but
yeah,
there is a factor of the velocity, the
uh-huh,
coherence velocity, which is the velocity which is greater than speed of light. If v equal to c, this becomes one, and it just becomes coupling. It's a coupling coefficient alpha.
yeah,
So essentially it depends on that, how this energy density changes. So the energy density locally can increase. That's what it means, right? So you
uh-huh,
have a general energy density, and you know about vacuum energy, all that could be
yeah,
an average level, but the locally can have higher energy density, and this
right,
higher density can create this particle, right? As you
Yeah.
increase more and more energy, it converts into particle. So, and
Yeah.
that's essentially the whole point. So, how it just does that is given by this equation. It depends on the magnetic field and all that. So,
Okay.
essentially, that's all it is. So, in the
Gotcha.
condensed state,
Very interesting,
yeah,
though.
yeah.
Okay. Move
So,
on.
high
We can move.
magnetic field is possible. Yeah, yeah, like 10 to the power minus power 18 Teslas, very high magnetic
Yeah.
field.
Uh-huh. Yeah,
So,
for sure. Yeah. That's interesting. So we can move on then if you like.
so this is again the
Mm.
next level. Euclidean action. From this, you can figure out gamma QCD as a temperature, how that changes. So you can, as you increase the temperature, uh, how the baryon production depends on this one. So as we
Okay.
know, the energy density creates that baryon eventually, and the temp as the temperature changes, as the energy density changes, so does the temperature, and so you have a coupling between the Euclid action and the temperature, and
Mm.
that changes the barium production. So it is a what you call a synergistic effect, you may call it, that you have both the temperature increasing it and then the barium production. How that happens is a non-linear effect. So they are opposing mechanisms, but there is a critical level of temperature above which uh, you know transition occurs. Um, so uh, so if it below a certain level, then you have the tunneling unsuppressed, the significant efficient baryogenesis. Uh, so the temperature is a very important thing. So it tries to keep certain temperature above certain temperature. Again, you have this Euclid action decreases if you keep increasing, and so the medium production is directly related to this Euclid action. So, so as we know, it's a negative effect. So as this uh, decreases, then E per minus SE increases, and so barium production rate increases. So as we increase the temperature, the barium production rate increases. Very similar to Arrhenius equation. Very similar thing. Exponential effect of this Euclid action.
Mm.
So, and it's a
Well,
negative. See, it's a negative sign. So this means that if this decreases, this increases, right? So essentially, that's how we get. So it's a non-linear effect. It's not a direct thing, but using this, we can show a barrier. We cannot immediately say conceptually how the temperature can increase the barium production rate. We cannot imagine that. By using this technique, Euclid action, we can see how that can increase it. Uh,
mm.
so we need this kind of formula. It's a synergistic effect. Because of that, we need a proper equation in order to figure out what's going on. Any non-linear effects, we cannot think. It's very hard to think with the common sense what's going to happen. It can, if it's a linear thing, yes, the common sense works. But this is the same thing I was going through my courses from bachelor level to graduate level, the Arrhenius equation. So that I cannot, really comprehend or mentally figure out, because I always try to, young days, I try to figure out very simply, simplify it to a quantitative conceptual level. And it's important. That's important because eventually it has to explain at that level the logic. Because we can think of the logic. That's a much simpler logic. I think nature operates like that. But the synergistic effect, there are many things interacting. Then how they interact, like a probability thing. Like you are toss a coin, right? You are head or tail. But if the next level, many coins are tossed, then how do you figure out? So you have probability, which you cannot comprehend by normal thing. So we cannot conceptually say how that is. So statistics is no longer valid. The probability takes. Probability, of course, is a more complex equation, and I always had a difficulty wrapping my head around that. I figured out it's a multiplicative effect, right? Mostly multiplications. So you have many combinations possible, and multiplies. So it decreases the probability. The multiplication decreases the probability, and that's the funny part of it. So if you have more and more events, possibilities like tossing coin head or tail, eventually it decreases and the signal to noise ratio decreases. It's a very important aspect. So that's
Yeah.
how we see more and more events. It will try to screen the effects of that,
The
effect of
decoherence or
one of
something.
them.
Or
Yeah,
like,
decoherence.
yeah,
Yeah,
interesting.
exactly.
That's very
So
interesting.
then
So
that,
I'm a little
yeah,
bit confused about the Euclidean action. Is that like some sort of Lagrangian or something? Or?
yeah, very similar to Lagrangian over time thinking. It is an action, right? So the action
Mhm.
is the ultimate thing that all the people are using.
Yeah.
Eventually, you what you call the Yukawa, not Yukawa, the other action. It's the most fundamental thing. So they found the action because it relates to Newtonian thing as well. Newton talk about action and reaction, right? So
Mm.
that's a fundamental thing. So
But how
anything
does
is,
it apply? How does it apply directly here? Because you have.
it's
So I
not
assume.
direct.
Uh,
It doesn't affect directly. See, that's the problem. These nonlinear things you cannot directly couple to Newton. Eventually, I think there will be a relationship. I think.
but
What we are
is
implying.
there not a direct relationship there between the Euclidean action as the for the exponential is approximately equal to the number of baryons? Isn't that correct?
Yeah, exponentially. Yeah. So it is a
So
rate of the primary.
that is a
It's a
direct
rate.
relationship, isn't it?
Yeah. So direct relation to, but exponentially related. Exponentially
Okay,
negatively related to the action.
but that's still a
That's the,
relationship, though, isn't it?
yeah. There's a relationship. Yes.
Didn't you just say they weren't connected?
No. I said Newtonian. The Newtonian action. See, the Newton's law. It's a very simple formulation, right? Of action
Oh,
and reaction. Of
okay.
force. How the force is causing the action. How
But
Newton
is yeah. So
rationalizes.
the action in a well, the action in a Lagrangian is some sort of it like returns it back to initial conditions, doesn't it? Which and
Yeah.
so then
So,
when we talk about action and reaction, I suppose that could also be returning to initial conditions as well. And
yeah.
some it doesn't always have to. Well, I suppose it does in terms of energy and
Elasticity.
stuff. Yeah,
Yeah. It depends on elasticity. For example, you have spring, right? You pull it
yeah.
out, and then it extends, and you let it go. It comes back to the original thing, right?
Mm.
It depends on elasticity,
I'm just
right?
wondering why does so you're talking here about you have a certain amount of energy maybe, and then some of it's converted into baryons as the temperature increases, and so
Yeah.
that's the kind of action you've got the energy turning
Yeah.
into the
Yeah.
matter. That's
Yeah.
interesting. And so as your temperature increases here, that would be like what as the universe is getting more dense at the
Hotter.
singularity towards the black hole or something.
Yeah. As it become hotter and hotter, right? We have the
But
epochs,
at
right?
at what point though? Because presumably the universe is what hottest at the singularity, or
Yeah.
maybe temperature doesn't mean anything at the singularity. But
Yeah.
then, so as it grows, is it cooling or is it getting hotter?
Yeah, then it goes through a cooling phase. So you have the inner
Yeah,
plasma, highly, very hot plasma. That's where the quark gluon probably is happening thing, the quark gluon type of
right.
thing is happening. But as it forms, see anything that once it forms, like even very hot liquid becomes a solid, right? Uh, at the interface. What happens is that when it forms, it's absorbing all the energy because matter has c square times what I call I mean divided by it divides the energy by c square, right? So the
Yeah.
matter is contained, it's condensed energy, highly condensed energy. So
Yeah.
when it forms, it is absorbing all the energy. So now there is no more energy outside. It's outside of that, the temperature drops like anything because there is not much energy there. So it cools down, you know?
Yeah. So see, so the temperature is increasing, and then all of that energy is being converted into matter, and then the
Yeah,
more matter that gets converted, then the more the temperature is going to drop.
yeah, yeah,
So if you were to continue on your graph here, I suppose you'd see it would sort of invert again or something like that.
yeah. At this critical ranges. So there's a critical range. There's
Yeah.
a critical temperature range at which it can cross, it can do either side depending on.
Well, it looks like your critical temperature range, or well, it's on the Euclidean action. It's 1. Is that not right? The
Yeah, it is.
critical.
Yeah,
So the yeah. So once the Euclidean action crosses 1, or the temperature goes critical or something. So the critical temperature then is around 200 MeV or
yeah,
whatever.
yeah, yeah,
Not sure I completely understand that, but it's interesting. Yeah, and
yeah,
then so isn't there like all of these kind of eras, like with the standard conventional cosmology? You've got like inflation, which would have cooled things down rapidly, wouldn't it? But then
yeah,
again,
yeah. There's a
yeah.
yeah.
But then you have this
They
like
say
era of recombination. So I think that's where the what is it? The neutrons and the electrons maybe
yeah,
come back together
yeah,
to form atoms or something. So
yeah.
is that all way distant in the future from this graph, or where does that take place? Where does this
Okay, you
graph
have
take
the.
place in terms of the time
No,
it's
I
from?
didn't put that the form the standard thing that they show a picture like that, right? Something like that
Yeah, I think I
for
know what
the
you mean.
for
Yeah,
the epochs. Yeah, I can pull out. We can pull out that in Wikipedia, but essentially it goes like a ellipsoid. What you call that? Hyperoid. So
yeah,
it's
yeah.
an inflation thing. It's a inflation thing which goes like this. So at this phase is where this is happening. At the
So
QCD, which is the quantum thermodynamic thing.
this is how this
It's
happens right
emerging.
at the beginning of the universe or something, doesn't it?
Yeah, yeah.
Okay.
At the and then the epoch then goes further
Okay, that's
as
fair enough.
the
Well, there'd be a lot of complicated stuff going on there, and also it's
yeah.
not well really understood, is it? So that's interesting. This what's next? Do you have more slides, or probably that's
Yeah,
about it? Yeah,
yeah. It's essentially, yeah. Essentially talks about again the threshold and all that. Essentially,
mm, okay, and the
how it
next,
inversely with mass and everything. So this is the quantum cellular thing that
yeah,
most recent one.
great.
Uh, that's the next level. What happens, how it, how ha- the baryons get locked up as
Mm.
hadronic lattice.
Oh yeah,
So how it forms a discrete space-time, for example. So again, it's a discretized space. So it's not a normal continuum. So essentially,
mm.
again, it's a discrete action. Again, you have Lagrangian action, things like that comes into picture. The discrete Lagrangian. Uh,
Yeah,
over and over again, these things will come, but they are the most important thing. Uh, so
fair
that
enough.
and
Oh
yeah.
yeah, this
So
was
now,
interesting. So you're talking about
yeah,
this time reversal thing,
yeah,
and then you bring in CPT and all of that. I'm just
yeah,
wondering. I was thinking about this over the week, and you know how,
uh-huh,
or just over the last while. You know the way you go down into the quantum realm, and they say you have this time irreversibility aspect, where if you ran it the other way around, it would still work and all of that.
Yeah.
But I don't think they mean that time is actually flowing in both directions. Are they saying that? Because obviously
Uh,
Feynman would have said that like antimatter is traveling backwards in time,
uh-huh.
but that's very difficult to defend, I think, reasonably. Or what do you think? Are you of the opinion that it is actually reversing? Time is actually flowing in both directions beneath a certain scale.
Yeah. The reason is there's something called tunneling. So
Yeah,
you have a barrier like a firewall, right? So
yeah,
essentially, what happens? The energy is a what you call as the degenerate energy. So on one side you have on the other side they are same energy, which means
right.
that they can just tunnel, which means that there is no time. Instantaneously, they can switch sides. So you can think of like a switch between this
Well,
and
I
that
don't know.
switches.
Does tunneling need to be instantaneous? Oh, if there's equal energy on both sides, you're saying that it can be
Yeah,
instantaneous. Oh,
yeah. It's like an entanglement almost.
yeah,
So
yeah, yeah.
we can switch sides. So the antimatter and that's why I think, again I had to develop this idea about eventually, but the idea is that antiparticle particle they can switch with each other. They can kind of what do you call transfer to each other. Oh, I am the same energy as you, so there is no difference between you and me. So I'll go this side, you go that side, type of thing. So
Okay, why is it? So you're just extending it to antimatter, then you're it.
yeah. I mean, I
Yeah.
don't bring it that here. It's more like time
Yeah.
reversible from the more
Okay.
fundamental aspects.
So do you think? So then answering the question, do you think it's because like in CPT when they talk about time reversal, they're talking
Uh-huh.
about like well, it's the same thing, really, isn't it? They just say, well, if we were to rewind the clock on the universe, uh,
Uh-huh.
everything would be the same because on the quantum level, you have this backwards thing going on.
Yeah.
Um, but so I mean, I would interpret that as like they're not saying that time is actually flowing backwards on small length scales, but I kind
Mm.
of got the
Seems
impression
like.
that you are saying that. Are you saying that? I don't know.
Well, okay. So interesting aspect you brought out last time about parity, chirality, and parity. So I think you mentioned that I should work on that. Actually, I started a project on that.
Mhm.
I'll probably eventually, after
Yeah,
publishing
because
a couple of
it is an
papers,
interesting question. I mean, can the parity extend to things like spin and then, but
yeah,
like,
that's I'm
but
looking
probably
into.
not. Maybe it's just talking about parity in terms of right and left-handed because I think that comes in a big way when you're talking about
Yeah,
uh, particles and antiparticles. If there's
yeah,
yeah, there's a big thing there, especially to do with the weak force and beta decay
yeah.
and all of that. If you reverse it,
Uh,
it's very obviously different. But I don't know. Well, that is interesting. And so
uh,
you're down to this length scale of 10 to the minus 15, which is what about the
yeah,
radius of
critical.
an electron, is it?
Yeah, electron. We are still subatomic. It will be
Yeah,
still subatomic, but we are in the range of a lattice, which can have, for example, electron lattice, if you can think of, electrons just made of electrons, uh, and that has like a Bohr radius is somewhere around the
yeah.
classical radius.
I like
So
that.
in that,
The minus 15. Yeah. Okay, but then you got this. So you're talking about a reversible microcircuit dynamic. So if you're saying it's a microcircuit, you're saying that this is a real physical thing. So is it actually reversing in real time, or is it just the reversibility is just maybe an abstract concept? But the microcircuit you're saying is a thing, is it?
yeah, you can think of like I visited here Grand Canyon. So you have a horseshoe bend where the water reverse goes around
Oh
and
yeah,
reverses. So very similar to I compared now. Recently I thought about how the sea reverses its course. So everything now we act, everything is separated as pure water we can drink and everything, right? Then everything's mixed up with all the, excretion, other things, and then goes back into the sea, right? Everything's like a cognate sea. So now it is like quantum thing. Like you have the micro level, it goes there, right? The micro level it goes there and reverses itself so it can start cleaning up. And then you have creation of this one to create a storm and the water that, evaporation process. So you have a condensate. You can think of a sea as a condensate, and you have the evaporation process again to clean up the whole thing and then create a very pure state. So in quantum, we talk about pure state and mixed state, right? It's a very similar thing here. So when you go to quantum level, you can go to a pure state and you can separate out the components in terms of
Is the pure state not
what it is.
just is a pure state not just like one choice in a metric direction? And if you took a
Yeah,
different one, you'd have a mixed state. But
yeah,
so like I don't know about that. I think like maybe pure and mixed aren't really that. It's no different than like some sort of rotation around a thing. I don't know if it
uh-huh,
means that it's no longer like it's equivalent to something that it's contaminated. I think
uh-huh.
all the states are correct, are they not?
Yeah, micro states. You can think of micro states.
Yeah.
So you have macro state is a combination of micro states, right? And
Okay.
when you do the probabilities, you have, you put the probabilities start decreasing, like we mentioned before. Probability is a multiplicative function. So you have many, many micro states. The whole signal to ratio decreases and becomes almost like a noise, right? So the macro level is becomes a noise, whereas the opposite happens when you go into micro states. Now it starts increasing, like we take out one by one. The signal to noise increases, so now we have radiation. It's like a laser, for example. When you see a light, it's diffused, but we go to a laser level, like a sodium vapor lamp, you have clear demarcation between the wavelengths, and that creates the laser effect. And this is now proved by laser devices, things like that. So that's
Mhm.
one of the proofs for the quantum mechanics, right? When you go to that level, you can differentiate and create very pure light, very pure laser, which has a
Oh
very
yeah,
high
I'm not saying
energy.
that there isn't possibilities for differentiation or anything. I'm just saying that there is the fact of the matter that superpositions exist down at the quantum scale supposedly,
Uh-huh.
and just because something has two states at the same time doesn't mean it's. I don't think that means it's impure. It just means like if this is one pure state, and then this is another, being halfway in
Uh-huh.
between, it's a mixed state. But I don't know if that would.
Yeah.
I don't know if I'd use the analogy pure, impure in terms of like whether water is clean or dirty. I mean, it's interesting, but I've never
Very
heard of.
simple analogy. Yeah. It's actually highly
Then
simplified.
you also seem to be linking that in terms of like a reversibility thing, but on a macro scale, um, w- the water does not, because of entropy, the water does not go back. It
Yeah.
doesn't condense backwards into the sea and then go flow back up the river and then back in,
Yeah.
into
Exactly.
where. So, so I think maybe the reversibility is on the small scale. So, what is the idea with the microcircuit? Where did you introduce that at this point?
Yeah. The quantum level. You had because
Well,
it
where
doesn't
where
have.
did you in the slideshow? Where do you introduce it first? Is it this slide?
Yeah. Actually, it's more detailed, so I didn't put it here. So in the paper I have, uh, I go into the microcircuit more detail about paper. I think I can pull up the paper maybe. Should I
Well,
pull up that?
yeah. No, I'm just asking. Where do you introduce it in this slideshow? Do you introduce it in this slide? Is this the first time we hear about it?
Yeah, 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 yeah.
Okay.
Because I'm just,
So what's the next
I'm
slide
just
then? Because
okay.
you talk about the microcircuit quite a bit. This one.
Yeah.
What are the axes on this graph?
Essentially, the defect structure, two-dimensional defect structure. So it's one dimension, another dimension. So it
So
is.
what is it? A space dimension? Is it just x, y?
Yeah,
Okay.
yeah. This is a phase dimension. This is the x dimension.
All right. But is phase not coming out towards us?
The phase, it's a two-dimension. Yeah, it's like a slice that coming out. So if you slice it, so
Well,
if you
the
go to the
phase
next
is
level,
the phase is the
it's a
color.
slice of it.
Well, no, go back to the earlier one. The phase is the color, Rajan, isn't
Yeah,
it?
so different colors. You can see
Right.
different
So,
colors.
what are the x and y axes on your graph then?
Okay, that's a two-dimension. Like you have a square, or they are the same, but essentially dimension, two dimensions. Like you have x dimension, y
Okay,
dimension,
so let's
right?
say you've got 0 at the bottom here, and then it goes up to 30 units. What are the units?
They are actually arbitrary. They are arbitrary unit. They are not on scale like centimeters or anything like that. They're the micro level. So
It's
it
some
will be
length
like in
scale
the,
though, right? So and then you've got
yeah,
another length, and
it
then
will
the
be in
other thing
the,
is the same. It's just a different length scale. So I'm not really
yeah,
so right. So you've got as you have this space, and as you move through the space, you're gonna encounter different intensities of phase. Is that it?
yeah,
Okay.
mainly.
All right, and then this is phase. Right. So this is how the kind of lattice is created. So is
Uh-huh.
it a bit like an interference pattern?
Yeah.
But it's a right. It's coarse grained. That makes sense. And then stable phase defects and vortices, emergent microscopic circuit elements absent. Yeah,
Essentially, it's like a wave function,
the mad scientist kind of thing. It applies here, I think, Rajan. Anyway,
Okay.
that's good. It's
So the
interesting.
idea is that the
Yeah.
defect, the main point I'm bringing out, the defects makes this irreversible, essentially. The defect, the
Hmm.
creation of these defects makes the thing irreversible. So it cannot go back.
Oh,
You know?
yeah, you mentioned that. I don't know why that
Yeah.
would be the case, though. Is it because of the decoherence thing again?
Yeah.
Okay,
So yeah, the coherence is lost. You need a coherence to create a reversibility.
that's
But
fair. That sounds
yeah,
reasonable. Let's move on to the next slide. This is the three-dimensional version.
version of that.
Yeah,
So
so it's basically the same thing, isn't it?
same
So
thing.
you
Yeah.
have this microcircuit elements, which are the reversible thing. Yeah, and then measurement-induced decoherence. So they're interfering with each other. And
Yeah.
then topological defects, stable. Yeah, that's what you said earlier, providing persistent, irreversible. Yeah, so it's basically you're just talking about decoherence on a quantum
Because
scale. Yeah.
it's a more expanded,
And
more what you
that
call.
destroys the irreversibility. But does it though? Because if I go down to that level and I want to say, all right, I see this reaction happening, and it goes, let's say it's electron pair production or something. So photon
Uh-huh.
splits into
Mm-hmm.
an electron and a positron, and I see
Mm-hmm.
that happening in real time. Now, if I want to
Mm-hmm.
reverse that mathematically or whatever, I can do that,
Mm-hmm.
and it works
Yeah.
out the same. But it's
Yeah.
not so even with the decoherence here and the if we notice let's say this is a bubble chamber and we see the particle the pair production occurring
Uh-huh.
that's happening in one direction, but
Uh-huh.
I can still reverse that process mathematically. So how is it really irreversible?
Well,
So
actually, it
it
is.
seems to
There's
suggest that you're saying that physically time can move backwards on a quantum scale, or before
yes.
decoherence occurs, there is no such thing as time. or something.
Yeah, that time is very, very small. So,
I don't know.
and I
You'd
have
want
done,
to, yeah, you'd want to prove that though, wouldn't you, before you even embark on this, or has it already been proven? I don't know.
yeah, the 10 to the power, I think a few papers occur, which they have shown 10 to the power minus 23 seconds, right? That's
Yeah,
the reversible time. So if we go back to that level, suppose you can hold it at that level, right? You have to
yeah.
hold it. If you can hold it at that level, then you can reverse time. See, the
Oh, yeah.
main thing
You've
is
been
can you
talking
hold
about
it?
this.
Can you hold it? Because
Yeah,
if you try to
you've been
decohort,
talking
you try to
about this, haven't you, for a
the
while,
environment
where
will not allow
you
that.
might be
Yeah.
able to reverse time, but it has to be at a you need very small amounts of time,
Yes.
because then
Yes.
the decoherence. Yeah, that's an interesting point. But I wonder if that's true, because I mean that sounds like it's very connected to um, what's his name, the uncertainty principle guy, Heisenberg.
Ah,
Uh,
Heisenberg.
yeah, because you know the way it's like, uh, if we measure the position exactly, then
Yeah.
its velocity is infinite. But if we measure the velocity accurately, then its position becomes infinite, because and it's like if you're measuring the velocity very accurately, you're getting down to like smaller and smaller time intervals, essentially.
Hmm.
So the particle then goes past your aperture, and it goes past almost at an infinite speed. And then the same
Hmm.
thing with the if you're getting to position, you're also narrowing down, but in space. And then so the velocity there term goes infinite. Oh, I should have said it the other way around, but you get the
Hmm.
idea. So I
Yeah.
mean, I
Yeah.
think it's a bit like if I'm looking at a car driving along the
Hmm.
motorway in the
Hmm.
distance, it looks to be
Hmm.
going very slow, and I can figure out
Hmm.
its speed. But if it's going by, and I've got a very narrow window, and I'm very close up to it, or let's say I've got an ant on a in a in a slide, like I've got pressed in one of these microscopic slides, and I move the slide across the bottom of the microscope. It looks like is moving very quickly, but it's actually just moving at a normal speed. It's not going as fast as the truck or anything, but it looks like it's going faster. So I wonder if there's this kind of weird trade-off. And then, in physics, they always talk about if you can't measure it, it doesn't exist. You know that idea?
Hmm.
Um,
Yeah.
and so,
Quantum mechanics also says that. Yeah. In a way.
yeah, yeah. This is in the quantum mechanics thing as well. And so if you can't measure it, it doesn't exist. So then when they do measure something, like in quantum with the Heisenberg uncertainty principle, they say, oh, this exists, rather than just saying, well, maybe this is just an effect of our measurement because of the
Hmm.
scales we're working at. And so, do you get the point I'm making then? Is that it relates back to what you're saying about this time irreversibility at a very small measurement scales. Maybe, like, if I was to videotape raindrops falling onto a
Yeah.
puddle, now if those raindrops are small enough and they hit the water and just generate like a flash of a circle. Do you ever see
Hmm.
that? Where it's just like
Yeah.
uh,
It's
it's
like
happening
the
so
waves.
quickly that it's
It's
just
like a
like,
wave it spread.
yeah,
Like wave.
the wave moves out and dissipates so quickly that you just see a flat, like a circle. It just goes boom, circle, and then over here another
Yeah.
raindrop, circle, and then the circle just disappears. And so if you were to
Uh-huh.
reverse that, it would look identical, because the circle just comes into being and then clips out of being again. But if it's a
Hmm.
larger raindrop, then it's going to create a bigger ripple, and that ripple will move further out, and
Yeah.
you will be able to see the path. And then if you
Uh-huh.
reverse it, you'll be able to see the path of the ripple going inwards. So now
Uh-huh.
time irreversibility is broken because we have a
Hmm.
larger sample set. So I would
Hmm.
say that if I had better eyes that were able to pick up movement
Hmm.
on a faster scale, even with those
Hmm.
tiny raindrops that create little ripples, I would still be able to
Hmm.
see. I would be able to see that process evolve, and therefore if I had better eyes, the time irreversibility wouldn't work at that scale. I would need even smaller raindrops and smaller, and that's where we get to the quantum thing. I think we're just bumping up against our resolution, and that it's maybe this time irreversibility thing is just nonsense and a product of people trying to say, well, if we can't detect it, then whatever results we're getting, we have to say that those are concretely those results. And maybe they're correct. Maybe at a certain level, you do get to a point where the resolution of the universe essentially clips out, and it doesn't go on for an infinite continuous process. So it is interesting. I'm just discussing the question really, rather than stamping an answer and saying, I'm right or they're right. Yeah. So it could, but it could be, couldn't it? It could be continuous, or do you think no? The Planck limits and all of this. Somehow we move into a quantized area where the frame rates are. I don't know how to bridge the analogies at this point. What's going on? You've got these quantum jumps. No continuous. You don't see the continuous ripple forming out. It's just a jump. It's just boom. It exists, and so therefore we can reverse it. Is that what you think? Or does that make sense?
You can think of like a step function. That's why memory effect also, I think, is important. Like a step function. So you see that how do you go from, if you have a step function, you need like a jump, right? I mean, if you are going up a step, if we keep going in the same way, we cannot go up a step. We need to jump it. So it's a different function altogether. Jumping is a totally different than a linear motion, right?
Yeah.
It's a non-linear motion. So you have to step it, which means that it's discontinuous in that sense. Because at the Planck level, you have many steps that going on. Which means how does it go from this step to this step? How does it jump to that step? That's the whole. So you have to supply enough energy. This is what Planck also says. You have to supply enough energy to make it jump to the next level. If you don't have enough energy, it doesn't jump. Essentially that's
well. Here's another way of looking at it, Rajan. Let's say I'm looking at that puddle again,
yeah.
And the raindrops are small, and one raindrop hits here, another hits here, and another hits there.
Yeah, I cannot see because I am in this screen, so I cannot see.
Okay, well, just imagine a clock face. One raindrop hits at 12. One raindrop hits at, let's say, 5 o'clock, and one raindrop hits at 8 o'clock. Okay. Now, and it does it sequentially. It goes 12, 5, 8. Now, if we reverse that, and I mean, I'm not saying that it hits at different times. Well, they do hit at different times because they're happening one after the other, but the spaces at which they hit are located at 12, 5, and do you get me? So it's like it's like a it's like a coordinate system. We're using it as the clock face as a coordinate system rather than a time system, right? So if we were to reverse the time, we see no difference. The raindrops look the same because we can play it backwards and forwards. It doesn't matter because of the discontinuous nonlinear step function you're talking about, where it flashes and it's gone. So we can play it backwards and forwards. It looks fine, but we notice that the pattern of events, instead of it going 12, 5, 8, it now goes 8, 5, 12. So in that sense, it's not actually. We can reverse the process and everything looks fine, but the events still happen in the. Do you know what I mean? Like. And that's kind of obvious. Anybody would say, well, yeah, you reverse time, the events are going to happen backwards. But my point is that it's not indistinguishable then. We can still say it's happening backwards. And the point I'm making is that I don't think we do see that like on a quantum scale here with your lattice. If there was quantum events occurring, and we could say, well, they do appear to be reversible, but if they're happening at different moments in different parts of this space here, then those will be distinguishable as reversible. Correct? We'd say.
Hmm.
So I don't know. Maybe that's
Essentially, I think it's an environment effect. If the environment gets into in the mix, then immediately that the coherence occurs. It will not allow any kind of reversibility.
well. That
So you
makes
have to
sense.
prevent the
So you're
environment
saying
acting.
that with the environment being space and time, correct?
Yeah, you
Or
can say that in general. Yeah.
yeah, I don't know. I suppose yeah, it's interesting. It's confusing though because I mean, space and time, what you'd imagine, are intrinsic to the quantum process as well. So even in the Schrodinger equation and such. Okay, so any more? You're talking about macroscopic degrees of freedom. Yeah, I think that's really it, isn't it? You kind
Yeah,
of
that's it. Yeah.
right. Well done.
That's the
I don't
current
have
state.
really.
Yeah.
I don't have a huge amount to show. I don't
Okay.
think. I mean, we could spend some time. Do I have to?
So I'll
Um,
get off this.
yeah. Okay. Yeah. And like I say, I feel pretty rough. So, but that was really good, Rajan. I thought that
Oh, thank you.
I'm getting I'm getting more uh, idea about what you're talking about, and it's beginning to make a lot more sense to me. So
Thank
it's
you.
good.
Yeah, it's an
But
ongoing thing,
I still think there's probably a good bit that I don't understand. Like there's a high sort of learning curve there with a lot of that stuff. Okay. Um, so there was some like an old. Do you remember we tried to do this before? I was trying to do discrete simulations of gravitational fields, and um, just using very simple ideas, and trying to to have like an agent build up a path so that you could create a curvature, and then I was also trying to see whether the curve that an agent builds using, let's say, the Bellman optimization equation, how does that relate to just your standard 1 over r squared? And we can see there's a difference. So, um, and there was attempts, some of them weren't that successful, and then you could do other things where you have like a revolving sort of version. So the better one was to just, I think, to abandon the agent approach, the sort of reinforcement learning kind of approach where you have like a discretized space, and just use the like the r squared version, which gives you more. So there's the gravity well of the moon effectively, and then we have like the Earth and the moon, so you could put them both in the
Yeah.
same space. And then there was potential to move on from this into like 4 dimensions, and back to like surface tension gravity models as well, which are interesting. Um, so I think so. Oh, wait a second. So this is
And this is
this.
a new one. This is like a recent one. I don't know.
Yeah. So I'll show you the. So those were just the. These are the original kind of work things that I did, but
Are you applying for like postdoctoral thing?
that was,
So
yeah. I mean, I think that was obviously not a very. It was sort of
I
like,
think I don't think I have seen this. When did you put it? January this month?
that's a good question. It has the date, July.
Oh, July 20. Oh, okay,
Yeah.
about 6 months
So
ago.
I mean, obviously, it was very simple sort of stuff, and especially compared to, there's certainly no supercomputers necessary or anything like that. The idea was to kind of hopefully to generate decent kind of graphics without the need of supercomputers, which probably is a bit naive. I mean, especially if you're looking at some of these videos of, let's say, like a moon crashing into a planet, it's going to be made up of like lots of individual granular elements, which each have their own sort of gravitational field effect. And then when one crashes into the other, you're going to have like collisions and all of this. So that the point I'm trying to make is that the simulations run away in complexity very quickly. And that's why you need probably need a supercomputer to do it. Whereas I suppose my goals here are much simpler. I'm just, well, initially I'm only starting off, so I just want to generate the kind of, you know, in the first instance we tried all of these things, they basically failed. So and then we just get back to a smoother sort of thing. So in the first instance, it was like, can I generate this? Can I do it for two objects? But we're still in only 2 dimensions here. So the next aim then was to sort of move out of that into the 3-dimensional space. So I think some of these are taking a long time to run. I think if I close that, was it not? Yeah. So these are the ones that were more. This is just the notebook that deals with this stuff that you saw in the, you know, the curvatures and the comparisons. I think, and then we get into those things. Yeah, here you can see the simulations, and then final one is where we bring in the second body, and then you have that. So there's also something weird where if you take this as gravity field and you flip two of the sort of features around, you wind up with a different effect, which is like this, which is interesting. You know, I was thinking maybe that'd be cool from a time point of view. Maybe this is like slices in time, but it didn't really pan out that way. So I kind of abandoned that. I went more towards the looking at 3 dimensions, trying to bring it up from the 2D to the 3D. So I think we might as well go there next. That seems like the.
You get like a step function there also.
There is no step function here. It's more to do with you reverse 2 of the like there's something you switch around. Possibly how you maybe 0. So if you switch the 0 and the 1 here in the polar image, so you're basically just switching around the axes. Instead of getting like the normal funnel shape or you know, curvature shape, you're getting this thing, which I thought was interesting because it kind of reminds me of a log Z spiral kind of helix thing. And I always think of that in terms of like, oh, well, in the X direction, you've got time. So you're sort of moving up in a time stairwell, kind of almost like a spiral staircase. But the more I thought about it, I kind of realized, well, no, that's not what's happening here. So, okay, so let's move on to the 3D version. So the point is, you know, to make one of these kind of point clouds where you have, and this is using probably spherical coordinates by the looks of it. So, so what we want to do is unwrap that and then apply a z you know, an or squared or kind of interpolation over this. So we we have this, we unwrap it, we apply the R squared thing, and then we rewrap it. And the end result is, I'm not sure if it's in this. Oh yeah, it is, I think. There might be an error somewhere here that I need to fix. This recon stride, I think we can put 1 in there, and then we can go. So there we have it. So it's more, you can see that we have a gradient here where there's an intense gravitational field here, and then it begins to lessen as we go out. And then we just, if I can move this over here, and then we just wrap it back using like I think you use spherical coordinates or something for that, and you get the so that should be the strength of like the gravitational field for a spherical object here. But there's another one actually. I think I might be missing something. Maybe not. Yeah, no, I think I am. Yeah, there should be another notebook where it also shows how the gravitational field changes as you go inside the object. But I don't have that, which could make it difficult to continue with the research today, but we might do it another time. In this version, we're sort of flattening it down from 3D into 2D, and but the idea is that you're supposed to add the strengths. So that's not actually accurate at the moment. We'll have to fix that later. And so this section, this notebook here is kind of interesting because it's sort of moving moving the research on sort of in a slightly different direction, because I suppose the next phase here would be because we only have one gravitating body here, but we'd want to introduce the second one as in this case, but bring it up into 3 dimensions. So that might be another thing. But in another way, I was thinking of maybe abandoning this approach for the meantime, because more in favor of the spherical surface tension gravity model. I mean, so this is kind of interesting. We've got tetrahedron vertices. So this code should generate those, or maybe not. Yeah, well, we'll see. Oh no, that's not gonna. That's a different thing. So 4 planes? Oh yeah, so this is just how to generate a tetrahedron from using points. So we get this kind of thing. It's quite nice to look at.
Oh yeah.
Yeah, and then we can do it for the other platonic solids as well. So we could get so this is going to be so we have the tetrahedron. You can do the cube, obviously, the octahedron, the icosahedron, and dodecahedron. So should be the dodecahedron. Where's it gone? Oh, there. And I just like the way the computer kind of renders it. It's sort of funny looking. Looks almost like some low polygon computer game graphics you might expect back in the day. And then you can do the same with this is the octahedron, is it? Yeah, so it's quite a simple object. And then you got star tetrahedron would be that one. You don't really need to include that one. And the icosahedron just saves me having to type it in, I suppose, if they're already visualized. Is this kind of thing. So they do get a bit more chaotic as they go up in the number of vertices and faces. It does start to get a bit more difficult to manage. And there is an interesting thing here. So essentially, we're looking to recreate what we had in the simpler form where we have the line and then we transform it into the Cartesian image. We sort of the unwrapping of the polar using the polar transform, and then we just try and get this more and more complicated until we bring it back up to, instead of just a this could be like a circle, if you like, of 4 points, very rudimentary. We're going to go back up to an actual sphere. Not sure if we need to run this one. So yeah, here we have a circle, and well, this is actually a sphere unwrapped here, but using see, there's two different methods. You could either use polar transforms or you can use the spherical coordinates, and they produce very different effects, and some are useful and some aren't. So for instance, here, if we have like a sphere made of what are those things called? Well, it doesn't really matter. They're just it's like it's like what you have in that computer game, that voxels. Yeah. So it's kind of like voxels anyway. So if we use the I think the polar transform unwrapping, let me just check the code. Seems to suggest this is a spherical transform unwrapping.
Are they discrete?
It is discrete, yes, for sure. But so you see what happens when we unwrap it. Let's say we're calling this the spherical one. See what happens when we unwrap it with the spherical? You don't get a flat plane. You get this sort of very lumpy thing. It's kind of cool to look at.
Like
yeah, I don't know. I think it's kind of cool to think. Could you apply this to quantum mechanics in some way? Could this could it be like some sort of
spikes?
Yeah, like waveform or something. It's kind of interesting to think about, but it doesn't really help us here in the current thing. So if we're using I think this might be the polar transform, then we have our sphere. So it's kind of back to what we were doing previously. We unwrap it and then we stack this and then use the OR squared and then rewrap it to get the field. So we want to try this with something like a tetrahedron or a dodecahedron, but it's going to I haven't really gotten to that level yet. Oh, so here you can kind of see the same thing. If we use the Cartesian spherical coordinates, and then we can flatten it. So we do wind up with a flat thing, but as we can see, it's not actually. It's got a lot of structure inside it, so it is different from the plane. However, if we do want to unwrap this object and we use the spherical coordinates, or if we use the one that's going to just make it flat, it doesn't work. So we actually need to switch the spherical coordinates to get a proper answer on this one, as you'll see in a minute. So this is the kind of thing where first we just do it on a flat plane, and then, but that's not what we want to see. Just check. So we need the polar transformation. Yeah, I'm correct. So that's the thing. So in order for the spherical one, we needed for a perfect sphere, we needed the spherical transformation. But for these other lower Platonic solids, it's better to use the polar transforms, because we get, when we unwrap it, we still how do you say, we kind of conserve the structure of the spikes. So each one of these spikes here is one of these points on the end, and that's kind of cool. So it's sort of unwrapping it, but still maintaining the geometry in a weird way,
almost like a chandelier.
Yeah, I guess, and it's pretty cool. Like, you got the nice curves. So if we wanted to generate then a gravitational field for this, what we'd want to do is begin to stack these things up and then rewrap it back into this form. So, and apply the R squared thing field to this, and then we'd be able to see, oh, how does the gravitational field affect the faces, which would be down in these troughs, and how does it affect at the edges here, or at the vertex points, which are these topmost points, and what we'd find is that it's like we'd assume that the gravitational field is stronger here relatively to the surrounding space, and stronger possibly around the edges as well. And it would also be stronger down here, but not in this area. So that's the kind of thing. So you'd expect to fall towards the spikes in some sense, or towards the vertices. And so that's really all I have kind of so far, really. I mean, obviously I can show you a few other things, but I don't think I have too much more to show. Yeah, so basically the only thing here really left to do is, I think, no, right. So essentially the next thing to do would be to start to merge these different parts. And in order to do that, we need to identify certain aspects in the code and such. You can see this is like proper mass terms, and also it's a mass divided by volume. So it is attempting to be like an analog to what you were talking about, where you have the density matrices. So it's all sort of in the sort of realm of what do you call this? General relativity as it stands, but would probably be missing a lot of fine elements. And I certainly don't think you're going to get any memory aspect out of this simulation. And actually, I'm not even too sure how you'd apply that in the.
This is like the famous. It's called a lave, or what's it called? You use the, in Lagrangian, you break it, the crystal symmetry. You saw. I forgot the name of that. People use it a lot. Matrix.
I'm not sure. No, I don't see what I'm trying to get across there is that this is pretty. I would say that this is fairly rudimentary at this point, and I can come back to it at a later stage, but that's sort of the extent of.
Quite interesting. Yeah, thank you.
Thank you. Yeah, it is pretty basic, though. I mean, even.
Yeah.
I mean, obviously, compared to what you're doing there, Rajan, you're bringing in a lot of threads, but you also have you have quite sort of advanced mathematical things going on. Really, what I'm trying to do is, because I sort of struggle with that side of things, I was trying to, in order to bring it over to the computer, I was going to simplify it, but then hopefully in the process of simplifying it, the idea is to make it more understandable. But if you simplify too much, you could be losing out on important parts of the actual framework that need to be in place in order for it to produce something meaningful. And that's really the question that's where it becomes difficult, because if you're trying to operate in a simplified area, but you simplify too much, and you're simplifying in the first instance to sort of understand the more complex thing. You know what I mean? There becomes like a bridge between how do you introduce the complex elements that you need in order to produce a proper simulation, if you don't have those things in your model because it's too simple, then how do you know that they need to be in there? For instance, like this memory thing is one example, but there's obviously a bunch of others. So some of these can be included. Um, Another way, like recently, actually, some of the more recent work that I've done is I've gone back into. Do you remember when I was starting off with these like quaternion matrices that
Mm.
produced these platonic solids? So it might be like a cube or a rhombic cube octahedron. And then I was trying to say, oh well, this is the electron, this is the positron, and you can add them together to get different particles. So I was kind of looking back into that, and I noticed that, yeah, indeed, you could have like an electron and then a positron, and then initially I was like adding them both together in different ways. So one using like an XOR rule set, or exclusive OR and exclusive NOR, I think it's called, and but if you just use the exclusive OR one, I think you just generate one particle, and that one particle then would be the photon, and you can work out all the spins, and that works quite well. And you can also sort of take out the mass for the photon and all, because when you add these two different quaternion matrices together, they make the diagonal element all zero. So then you can get the trace for that and say, there's no mass in this particular interaction or in this particular particle structure. This is pretty cool.
Some
And
kernel or something, right? You call it kernel?
they might do. I think they call it a trace today. There could be.
Trace, yeah, trace.
So
Non-zero trace.
yeah, exactly. Because the other particles, the electron and the positron, both have non-zero traces. Although they do, I think one of them has like a negative trace, which doesn't make sense because antimatter doesn't have negative mass. So I suppose you'd have to take like maybe the absolute sum of the trace or something like that, which is probably fine. And then, yeah, so that's interesting. So we can actually build these, simulations where you have two particles that come in, they annihilate, generate the photon, and then decay again. And all of that is done through fairly simple mathematics. And you can take the Lagrangian of that and all, because there's no, it's not a point where there's a blow up or anything when you differentiate. So that resolves that. But obviously they already have solutions to that in terms of renormalization. But I think the idea here is that if you could, the idea is to like generate new models which might perhaps give a better understanding of things. For instance, if I was to extend that to, let's say, the quark model, or like the nucleus, so we're looking at beta decay, I wouldn't be able to have like three quarks that form a nucleus and then one of them decays into, let's say, an electron and a neutrino. All of that would be completely beyond the scope of this quaternion matrix platonic solid method. And the reason for that is because, so you would want a single particle that defines the proton, let's say, or let's say the neutron. Yeah, let's say the neutron. And then you already have your electron particle, and you'd be able to generate a simple neutrino analog or something. Then you add those together to the neutron, and then you would get a proton. But there will be no W boson, so electroweak theory is out. There's no three quarks, so QCD is gone. Therefore, the gluons are gone. So the whole standard model is out in this paradigm, which is interesting. So it kind of goes back more to, let's say, Bill's well, Bill doesn't believe in the standard model. Who else?
It's more classical, right? More like classical physics, closer to.
I guess, yeah, yeah. Because we're talking about actual things that are like blocks, that exist. Well, they don't have to be hard. They could be made up of lots of different points or whatever. It could be a point cloud, but yeah, and those points are also rotating, so you could have like a vortex. So it kind of goes back to that. The same with like the things like John Duffield's talking about, and also you know Unzicker as well. So a lot of people have this sort of, and I think even Emmanuel as well, if I'm not mistaken. He's kind of, yeah, he would be, because he works with Duffield, doesn't he, in the Zitter Institute? So it's all very similar. So that's really it. That's all I've got at the moment. I was thinking about maybe doing to see if I could code that up today and produce the let's say if you had a cube instead of a tetrahedron, we could get the mass of the Borg cube from Star Trek and see if we could generate the actual field for that, just for fun. But I don't think I'll be able to do that today because not sure when I'll get around to that. But hopefully not too long. Uh, okay, so Rajan, unless you want to talk about anything else.
That's it. So mainly, yeah, what I find is it's interesting. I mean, I go through like a elimination process. So, and I feel good about it in the sense that I look at different angles and then, you say those are not possible, and then you are not just hand waving, but actually mathematically, I want to have kind of a rigorous way. That's the mathematical. I think it's fairly rigorous. And each paper, I want that. Eventually, I want to put together and go back your original thing about beginning the chirality and parity and bringing them together, you know,
Yeah,
uh, and the time tensor and everything coming together. They're like components. Yeah, I see them like components of an assembly. So you are producing different components or the pieces of the puzzle and then try to put them together and then
yeah,
see whether they match or they mesh together, things like that. I think that approach is much better, I feel, because in the realistic world also you are assembling a computer. Think of a computer, right? You have you have the components which are resistors, capacitors, and probably inductors or whatever power source things. Then you assemble them together and then they work. So I believe in that kind of scenario that that's how you should build up. So then you can see the whole picture. So that's what I want to get, the whole picture. Uh,
mm,
because without that, I think it's all just curious speculations. So it's are important to start with, but eventually, something has to be real. Something has to or make sense from experimental measurements. And then, of course, Bill is saying that the experiment itself is invalid, and he goes even further than that and saying, you know, uh, saying that we are trying to frame things like time as we want to see it, but actual objects. He thinks about objects. So I mean, we are coming to very similar thing, but he think actual objects that you see, can you relate to that? That seems to be reasonable for physics. Physics is promising that. It's not unlike mathematics, which think of imaginary things. Physics says that actual objects, you work with actual objects and see how they interact. And so that's very interesting. I think, that's the elimination process I come through because you cannot totally remove the I, people, the Cartonian, like we talked about, or the imaginary things, because they are important. And the field itself, Bill doesn't believe in field. They are all nonsense, according to um, but I think they are necessary. They are like the intermediate step. It's like you make a scaffolding or some kind of mask. Like
Yeah.
even if you want to make an integrated circuit or anything ICs, right? Chips. You need scaffolding mask, but then you remove it, right? Very similar. The fields and everything are like that, but eventually you remove it and then see whether comes. So their intermediate step, like the root of -1, the imaginary thing is all intermediate thing. But once you put them together, then you can remove them. They're just, they're not objects, but they are uh, uh, entities that helps you to get to the objects. That's the way I see. So I think from that point of view, but it has to be concrete. You know, so you have to develop. So these pieces together eventually you want to understand time. That's my main one of the objects is to understand time. That even Hawkins was talking about
Mm.
brief history of time. And I think the quantum cellular automata, when I talk about time, it makes sense. So uh, that's where the reversible time again to put them together in the proper perspective, how exactly they work. If you can in the memory, see in memory it works. The reversible thing works. Suppose I am thinking and try to remember. I go back, go to the minute level. Then I pull out that memory, right? So that is the reversible aspect. Then I can figure out what I was thinking or what I was going through before, because that's important to connect. So from that point of view, the reversibility is important. So that's how I see reversibility as that go to the minute element. And the nature also does the same way. Black hole, everything, it pulls everything apart, the expectancy, and then make into fundamental ions or, even ions, it splits up and electrons and all the little particles. So we do that all the time. We call disassembling, kind of a disassembling of an assembly and then put them back together again. We do that. I mean, like we make iron. I remember making iron. That's my fundamental metallurgy. You have ore there. So then you put it in the furnace and then you bring them apart, right? You make into solid. You and then you remove everything except the iron and carbon, and then you combine them. So then you have pure iron, and then you add chromium, everything, and then alloy. So then you have structure, and the structure eventually corrodes and goes back to the original situation. So very similar. The nature works similarly. So nature combines everything together, then splits them apart. Even our body is very similar. We are all the things coming in, the bones and the flesh, everything. But eventually you die, everything pulls apart into nature and it disagrees into the environment, right? Even the trees, everything, same thing, and it all becomes very simple, uh, you know, thing of fundamental nature. So I think that process makes sense to me. How the process goes through high level order from disorder you get order, and again it goes back to disorder. So order disorder transformations keeps happening all the time in nature. I think that's what you have to explain eventually, and all these are important steps to rigorously prove and also see how they occur. So and then in that process we have applications. The computer, supercomputer, quantum computing, and probably next level AI. Then you have humanoids, which will eventually help us to extend our abilities to the next level. And I'm using more and more AI these days to research at least. And they are very quite helpful because it will take me days or probably years to do things that I can do in hours or days. So there are some extraneous meaningless things that come in between, unfortunately. Trivial things that come, a lot of garbage comes. But eventually we have to sort through and filter through that and get to the bare minimum, uh, and then see a proper. I think it's evolving. Initially I was not sure, But I think I am more confident after these things that in the future we can see. I can also see I was far behind when I went there, like decades behind, right? So I was not sure I can ever catch up in my lifetime. But I think I am not too far from now. I caught up at least the last decade. I wish I had done it a decade before. Previously, I used to think I should have done several decades ago. Now I think I advanced to a level that I wish I had done it last decade. But eventually, I think I'll catch up. And then probably last year I should have done. When we had the conference, I should have been at that level. Maybe in a year or end of this year, I may reach. I'm kind of feeling confident that I may reach that level. So you won't be too far from other people. Uh, the only problem is that many of these publications, when I put in the AI, it said that it's not in the you know uh, admitted type of journals like Physical Review and other things. But I feel that it's not highly standardized. It's not accepted as a norm yet. But I think eventually people will start noticing our research. I believe that eventually they'll start, there is something to it, you know. And I want to reach that level when it starts understanding these unresolved problems like CPT.
Well, yeah,
That,
that's a good point you raised there, Rajan, because I mean, I was thinking about that. You know how you might have like you might have a group of theorists or something who are working in, like, let's say, cosmology or quantum mechanics, but in a very, so in the, like, standard model in some sort of very conventional sense. But then they're like, oh well, we're happy to go over here and talk about string theory, or borrow some elements from quantum loop gravity or whatever in cosmology. They'd be happy to look at entropic gravity and all these different things, and they're happy enough to, and like if their own theory then collapses the main one, then they go, oh well, then we'll just move to string theory now, or we'll move to entropic gravity to solve the problems there. And that's kind of what I think. So that's a valid way of doing things. And like if they were starting off saying, oh no, we're right, your idea is wrong, and then
Mhm.
uh, and then and then it turns out their idea was wrong the whole time, and now they had to go to pick this other idea out of like the allowed ideas they're allowed to pick.
Mhm.
But how do they know if they were wrong at the base level about what they're talking about? How do they even know if they're right about these other ideas that they're allowed to choose from? Who sets those? Why is there such a limited number? Especially if it turns out that, well, your conception of the universe was incorrect from the start, then shouldn't you be open to all possibilities? And really the point I'm making there is that, like, all of these things should be just considered tools, like in a toolbox. I'm sure this has been said
Mhm.
many times, but you know how, like, we were just talking there, like I have possibly some theory with these platonic solids that go around and join to create other ones using quaternium matrices, but that and that's fine, but it seems to maybe rule out then some aspects of, or you can't explore, or it rules out some aspects of the standard model. And or so, like, let's look at this rope. I don't know if you watched the episode that we did with, I think it was myself and Bill. We're looking at the new rope model. Oh yeah, it was a synthesis thing. So I don't know if you watched that, but in that,
Yeah, when you're doing that, I watched on the sideline.
oh, that's right. Yeah, you did. Yeah. Okay. So that was good. We had these. So I kind of had these braided diagrams for different particles, and you could see that so you could do uh, electron pair production with that as well, where you have the photon and then it unwinds into these two other strings using this thing called a plectoneme, or a supercoiling and all that. But there's issues there as well, because like we were talking about with the mixing of particles, so you could have like um, a gluon one, or the the third gluon or whatever, and then you can have a mix between those two, which is like halfway between those things. But if you were to take the braids for those two particles and then try and find, well, what's halfway between those two braids? Well, if you were to do like an operation on them, just multiply them together, you're going to get a different braid, which is already a particle. It's not a, in the model I'm working with, it wouldn't be a mixture, it would be a different particle altogether. And then of course, so you could try to join up maybe 3 of the quarks, because they'd have different colors and all. Well, certainly I'd have to look into that, but let's say you can join 3 of the quarks together, and you could loop them in, like, I don't know, this is not really, I wasn't like prepared to talk about this. You see that kind of thing, or sorry, so there's like 3 loops on the ends, so they could kind of loop that way or something around. That's really bad, but you gotta get the idea. I think you've seen those things before, where it's like just like a loop like that. And then so you can imagine if we so with what is it, quark gluon confinement and all of that. So if you're like pulling on one of the, so if you're trying to break the nucleon apart by pulling on one of the quarks, although technically the quarks will be these things and the loops are the gluons, but either way, so you're kind of pulling, and the idea is the other 2 get really tight, and that's your confinement, and then they get so tight somehow that they like break away and produce 2 other particles. But those 2 particles would need to be obviously the neutrino and the electron, and those 2 particles have a specific braiding pattern, and it's unclear how you could get those braiding patterns out of the thing. So the point I'm making is that there would be big problems trying to move the chord model that I was working with the plectonemes into like a proper working theory of like beta decay as proposed in the standard models. So that could mean, again, that, maybe so at that point I'm thinking, well, does that mean that could be a falsifier for the theory, and that's good? Or you could say, well, okay, that only works up to this point, and then we could hand it over to like the rope hypothesis people, the rope model people, and then they can use that, so, or like we could borrow their thing and say, well, we'll just use their paradigm. In this model, there is no weak force, there is no gluons, there is no quarks, that kind of thing, so you just strip it down, make a simpler model, and continue on. And that's kind of exactly what I think physicists like are doing all the time. If their continuous Lagrangian doesn't work, well, we'll just use a discrete Lagrangian this time, so even though that's maybe allowed or not allowed depending on the thing, but if it gets the right results, then it's good enough, and stuff like that. So but there could be other criteria, if you are, there could be other ways of being disqualified, but I think essentially it doesn't really matter about whether you're getting published in like some big journal, because they're kind of expensive to publish in anyway. But it's more about, do you have like a good network of people around you? Do you have like tools you can use? And we don't need to say, oh, we can only borrow from loop quantum gravity and string theory. We have more options open to us, I think, and that's good, and it's more inclusive, and it's also kind of more fun. So so, and hopefully it's more understandable. Although I have to say, I think you're right. I think you are getting closer to this level of complexity that's needed for some of these publications, and that's a good thing. But it's also kind of a bad thing from my perspective, because it's like it's harder for me to fully understand what you're saying. But I do kind of get it. So, But it is good. It's also actually a bit beneficial because in some ways, it does clarify things. It makes it easier to understand. So, yeah, some more of that would be good, I'd say. And
I have two more in the pipeline. So, I mean, they will finish the components, but after that, I'll start. Then I'll rethink and then put them together and see. They like a piece of a puzzle and put them together and see whether it starts making sense.
yeah, I think
Going
if you
backwards.
are talking about this six rank six tensor and all that for time, it'd be interesting to see if you can do the same sort of treatment that you've done here with this work on that, make that
Yeah,
really concrete,
yeah,
then see if you can join them together or
yeah.
how that works, or
That's
if it
what I
needs to
want
be,
to do.
or if it needs to be abandoned or modified. Perhaps maybe you only need a rank three tensor, maybe you only
Yeah,
need a rank one tensor, which is what a scalar,
yeah,
I think. So or yeah, so or maybe you need a vector. Yeah, so those things you just need to try them out. It's pretty interesting though.
yeah. It's like
Okay, I better go
independent
get.
evaluator. Yeah, it's like independent evaluator. So you develop something and then look at from a different perspective, and then look at yourself and criticize that and see whether it holds up. So it's like hardballing or brainstorming, and you're looking objectively yourself, and you are not afraid to say that's wrong or right, depending on. So you are not fixed on some things, but it's a hypothesis, and you say my null hypothesis was wrong or false. Now I develop alternate hypothesis, and like that, the science moves like that. So it's a really objective way of moving. I think we should. I think you are also doing that. I think we should be in good shape. I think as we go along. Okay.
Yeah. Okay, so I think we'll on that note
Yeah,
leave it
sounds
there.
good. Thanks.
Okay, thanks
So
for.
let me see.